Have you ever just stopped, looked up, and really wondered about something you see almost every single day? Well, today we're going to do just that. We're going to follow a single beam of sunlight on its incredible journey from the sun all the way to your eye, just to find the answer.
You know the scene. You look up on a clear day and it's just blue. This huge, endless dome of calm, bright blue. It feels so simple, right? So permanent. But of course, it's not.
Because that exact same sky, just a few hours later, can look like it's literally on fire. It explodes into these incredible oranges and pinks and deep reds. I mean, it's a total transformation. So, that's our big mystery. The sun hasn't changed. And we know the space just beyond our atmosphere is pitch black. So where are all these colors coming from? And why on earth do they change? Well, the answer starts with the sunlight itself. It turns out the light that travels all that way from the sun is hiding a secret. To solve this whole mystery, we have to first understand what sunlight is really made of. To us, sunlight just looks, white, maybe a little yellow. But in reality, it's this high-speed cocktail of every single color of the rainbow all blended together. You can think of it like a rainbow in disguise. And the absolute key to understanding how all these colors get separated is this idea of wavelength. See, each color travels as a wave, and each one has its own unique size. This one property is going to decide its fate. So on one side, you've got blue light with its short, tight, kind of energetic waves. And on the other, you have red light with its long, stretched out, lazy waves. And as we're about to see, that short, tight structure is the whole reason this happens. It makes blue light super easy to knock off course. So our beam of rainbow-colored light is speeding towards Earth, and now it's time for the main event, its collision with our atmosphere. This right here is where the magic happens. Now, the sciencey term for this is Rayleigh scattering. But all that really means is that when light smacks into the tiny, invisible gas molecules in our air, it gets bounced around like a pinball. It's sent flying off in totally new, random directions. Okay, so here's the crucial breakdown. Sunlight hits the atmosphere, and right away, it starts crashing into air molecules. Because of its short, fidgety wavelength, blue light gets scattered everywhere. But those long, stable red light waves, for the most part, they just power right on through and keep going straight. And believe it or not, that one simple fact that blue light gets thrown all over the place is the entire reason our daytime sky is blue. So get this, the sky isn't some kind of blue ceiling or shell above us. No. When you look up, what you're actually seeing is a massive, glowing cloud of blue light that's been knocked sideways by air molecules and sent straight into your eyes from every single direction. The air itself is glowing blue. Okay, this is a fantastic question. You might be thinking, hold on, if shorter waves scatter more easily and violet's waves are even shorter than blues, shouldn't our sky be a deep violet color? And you know what? That's totally logical. There are two main reasons it's not. First, the sun just happens to send out a little more blue light than violet light. But the real clincher, the main reason, is our eyes. Our eyes are just built to be way, way more sensitive to blue light. So even though there's plenty of violet light scattering up there, our brains mostly just pick up on the blue. Here's a really great way to picture it. Imagine that the air is filled with this tiny, invisible dust. And this dust is constantly bleeding off blue light in every direction. That dust is the air molecules, and that bleeding light is what we see as the blue sky. And this also explains why the sun looks a bit yellow when it's high in the sky. By the time its light gets directly to you, some of that blue light has been stolen and scattered all across the sky. So you're just seeing the leftover colors, which mix together to look yellowish white. All right, so that explains the blue day. But what about that fiery red sunset? Well, it's the exact same science, but one crucial thing changes. The path that the light has to take to get to you. And here it is. At midday, sunlight pretty much takes a shortcut, coming straight down through a relatively thin layer of atmosphere. But at sunset, that light has to travel at a really shallow angle, forcing it to pass through a much, much thicker slice of air to reach you. And we're not talking about just a little more air. At sunset, the sun's light has to travel through several times more atmosphere than it does at noon. That means way more air molecules and way more chances for that light to get scattered. And with that much air in the way, the poor blue light just doesn't stand a chance. It gets scattered so many times that basically none of it is left in that direct beam of light that reaches your eyes. It's been completely filtered out long before it ever gets to you. So, what's left? What survives that incredibly long and difficult journey? Only the toughest, most resilient, long wavelength colors. The yellows, the oranges, and especially the reds. They are the only ones that can make it all the way through that thick wall of air to paint the sky for us. So when you put it all together, you realize the sky isn't really a static thing. It's more like a dynamic performance that's happening all the time. It really is that simple. The sky is blue because the air is full of these tiny thieves that steal blue light and just throw it all around for us to see. And sunsets are red because after that long, long journey through the air, all the blue has been stolen away and only the red is left. So, the next time you look up, just remember, you're not looking at empty space. You are watching a live painting created in real time by nothing more than sunlight and air, constantly changing its masterpiece from one moment to the next.